All right, so today we are going to be taking a look at the notes for speed and velocity and acceleration. So starting off with the definition of speed. Speed is the rate of change of distance. Now we always express it as a positive value, simply because speed does not indicate the direction of an object. So no negative sign would get associated with this. We just leave it as a simple positive number. Speed is measured in meters per second, and we will see in a moment that that comes from the formula of speed equaling the distance traveled divided by time. So v equals x over t, and this will calculate our average speed. Velocity, on the other hand, is very similar. Velocity is the rate of change of the displacement of an object. Now remember, distance and displacement are two different quantities. They do not represent the same thing. Distance is a scalar, representing simply how far you travel. And displacement is a vector, taking a look at how far you are from your starting point. Now, because velocity, derived from displacement, is a vector, the direction matters. For the purposes of these notes and for example problems, I'm going to be using this scale. Anything that is positive will be going up, right, or forwards. Anything negative will go down, left, or backwards. Velocity is also measured in meters per second, and it's calculated virtually identically to speed. The only difference is that velocity is the displacement relative to the time as compared to the distance divided by time. Now, the formulas for speed and velocity visually look to be the same. That's because they're representing the same basic quantities, although they are derived from different terms. So let's take a look now at some example problems. Our first example problem is this. A car travels 180 meters, then turns around and goes 40 meters. If the entire trip took 10 seconds, what is the car's speed and velocity? Take a moment to calculate those now. All right, so let's begin. Take a look at what we know. A car first travels 100 meters and then turns around going another 40 meters. So for number one, the car starts here, travels 180, presumably to the right, and then goes backwards 40 meters. This will give us a distance of the sum of these two values. 180 meters plus 40 meters, 220 meters in total. The displacement, on the other hand, is how far the car is from the starting point. So that would be 180 meters minus 40 meters, or a distance of 140 meters. Now, to get the speed and velocity, speed is the distance divided by time. Because we're using distance and displacement in this problem, I'm differentiating distance with the d as compared to using the x. 220 meters divided by the time, which is 10 seconds, that gives us 22 meters per second. While the displacement, while the velocity, on the other hand, I should say, is displacement over time, which is only 14 meters per second. So next is problem 2. When running along a racetrack, the runner speeds up from rest and runs the entire 100 meters. then slows to a rest over 100 meters. If this entire trip took 4.8 seconds, what is his average velocity? So this problem does not include the speed. We're simply looking at the distance, or the displacement, I should say, he traveled. So he started at rest and traveled 100 meters. And then it took him 10 meters to slow down. Now, the fact that he started and ended at rest is irrelevant to the problem because we're looking for the average velocity. So the displacement he traveled is 110 meters. The velocity is that distance divided by time. So this one you're going to have to go to your calculator for, unless you're really good at doing division in your head. 110 meters divided by the time of 4.8 seconds. His average velocity was 22.9 meters per second. So now we want to take a look at acceleration. Now, conceptually, we're aware of the fact that velocity can change. It doesn't stay the same the entire time, as we saw in the previous problem. And so this can be achieved in a couple of different ways. The first being that the object's speed can increase or decrease, or the object can change its direction, aka it can turn. The acceleration of the object is the rate of change in the velocity. And remember, rate means change over time. So this means that acceleration can describe the rate at which the speed changes, or it can describe the rate at which the direction changes, or both. Now, primarily, we will be focusing on changes in speed, although changes in direction, going from the positive direction to the negative direction, are entirely possible. Especially when we take a look at free fall, we will see those types of situations. Now, the unit of acceleration is meters per second squared, meaning that every second that goes by, velocity changes by a certain amount of meters per second. And we calculate acceleration by looking at the change in velocity over time. And remember that that Greek letter delta there, that V, or excuse me, that triangle shape there, means change. And change is always final minus initial. So let's take a look at a couple more definitions first. So first of all, when we use the term rest, this means the object is not moving. And it can be phrased in a variety of different ways, as you can see on the slide. Now, acceleration must contain the direction. Just like with velocity, this tells us the direction in which the velocity is changing. And we're going to use the same convention as before. Now, it's very important to note the direction of the acceleration doesn't automatically tell us whether the object is speeding up or slowing down. So, a negative acceleration simply means that the object is accelerating in the negative direction. It is not the same thing as a deceleration, because deceleration always implies the object is slowing down. But if something is already traveling in the negative direction and undergoes a negative acceleration, it will speed up because it's already going in the negative direction. So pay close attention to the directions of final velocity, initial velocity, and acceleration. That will tell you whether the object is going to speed up or slow down. And lastly, remember that time is a scalar, which means that time can never come out as negative. So let's take a look at some examples now. Our first one here says a car accelerates from rest to 25 meters per second in 5 seconds. What is the car's acceleration? So let's begin by taking a look at what we know. It accelerates from rest to 25 meters per second in 5 seconds. So since it comes from rest, that means that the initial velocity is 0. And the final velocity is that 25 meters per second. The initial and final velocities are very heavily based on the context of the question. And the time is given to us in 5 seconds. So once we recognize this, the problem primarily becomes a plug and chug. Acceleration is final minus the initial velocity divided by time, 25 meters per second minus 0 meters per second over 5 seconds. And this comes out to be 5 meters per second squared. Problem 2. When a runner passes the finish line, they slow down from their top speed of 32 kilometers per hour in 3.2 seconds. What is their acceleration? All right, so the runner is going to be starting at 32 kilometers per hour, and they're going to end at 0 meters per second. Now, this is one where we have to kind of gauge it based on the question. The runner presumably is going to stop after they finish the race. So that's why we're making the final velocity 0. And the time in which this is occurring is 3.2 seconds. Now, before we can calculate the acceleration, we have to convert the 32 kilometers per hour into meters per second. So remember, in 1 kilometer, there are 1,000 meters. And 1 hour is 3,600 seconds. So hours cancels hours, kilometers with kilometers, and we can solve this out. 32 times 1,000 divided by 3,600 comes out to be 8.9 meters per second. And so now we can plug and chug just like the previous problem. Final velocity minus the initial velocity divided by the time. So VF is 0 minus 8.9 divided by 3.2 will give us a negative 2.8 meters per second squared. And one more question. A model car speeds up from rest in 3 seconds with an acceleration of 1.2 meters per second squared. What is its top speed? All right, so the model car speeds up from rest. Well, the initial velocity is 0 meters per second. It does this in 3 seconds with an acceleration of 1.2 meters per second squared. And we're asked for the top speed. In this case, that would be the final velocity. So we're going to have to rearrange our equation. Acceleration is equal to Vf minus Vi over t. Now, since Vi is 0, we can take that out of the equation and multiply both sides by time. And there's our equation by itself. Vf is acceleration times time. So 3 meters per second times 1.2 meters per second squared, 3 seconds times 1.2 meters per second squared, will give us our final velocity of 3.6 meters per second.